this lab, we will investigate the reaction between the crystal violet cation, structure on the left, and sodium hydroxide. Our goal is to use a spectrophotometric approach to determine the order of the reaction with respect to the crystal violet cation. This molecular cation lends itself well to this sort of analysis. 3 dimethylamminobenzene rings chemically bonded to one carbocation results in the structure absorbing visible light at a wavelength max of 565 nanometers. The visible wavelengths not absorbed are reflected and result in a purple-colored aqueous solution. Through Beer's law, the absorbance of the crystal violet cation aqueous solution can be related to its concentration. Given that the product of this reaction is colorless, i.e. does not absorb visible light, we can monitor the progress of the reaction by measuring the decrease of absorbance at 565 nanometers as a function of time. While it is helpful to be aware of the complete molecular structure of the crystal violet cation, this chemical reaction is often represented in an abbreviated form as shown here. Cv plus is the purple-colored crystal violet cation, and CvOH is the colorless product. The general rate law for this reaction is written as follows. While our experimental approach can easily be used to find the order of the reaction with respect to the hydroxide ion, we are given a head start and told that this value, corresponding to the exponent n, is equal to 1. This tells us that the concentration of the hydroxide ion does indeed affect the rate of reaction. If we, however, set the hydroxide concentration to be 1,000 times larger than the concentration of the crystal violet ion, then the hydroxide concentration will essentially remain constant over the course of the experiment. Therefore, only the change in concentration of the crystal violet cation, as it is consumed, will affect the rate. A simplified rate law can be written where K prime is a pseudo-rate constant and is equivalent to the actual rate constant multiplied by the hydroxide concentration. Our goal in this experiment will be to produce an absorbance versus time graph which shows the consumption of the crystal violet cation. Using Beer's law, the absorbance can be converted to the concentration of the crystal violet cation. 3 related graphs can then be produced in Excel: concentration versus time, ln of concentration versus time, and 1 over concentration versus time. The graph, which shows a linear relationship, will correspond to the order of the reaction with respect to the crystal violet. Therefore, this approach will allow us to determine the exponent m. The experimental setup is shown in this diagram. 10 milliliters of 2.0 times 10 to the negative 5 molar crystal violet solution is added to a beaker. The temperature is recorded. The reaction is initiated by adding 10 mils of 0.1 molar NaOH. A cuvette is rinsed once and then filled with the reaction mixture. It is quickly transferred to the colorimeter. Continuous absorbance readings as a function of time are recorded on the LabQuest 2 screen. A second point before we get to the lab is related to the concentration of the reactants at the time of mixing. Note that because the final volume of the reaction mixture is 20 mils, both the crystal violet and the sodium hydroxide are diluted twofold from the original stock solution concentrations. This fact will be important as you present and process your experimental data.